Another tornado in April 2011. It destroyed a good part of the city, but not on my side of the river, so I wasn't affected by it, but I know people that were. Alabama is, at one time, was south of the equator, and here, and Tuscaloosa was on the shoreline of an ancient sea. And the reason I bring this up is because of the long look-back times we have in astronomy. Now, it's a great privilege, let's see, for me to talk about galaxy morphology at this conference. It's a rich subject. It's classical. It's got a rich history. And, of course, morphology is, in most extragalactic studies, it's kind of the first step in trying to understand galaxies. We think of them as fundamental units of matter and space. The subject is associated with many famous names: the Herschels, the Third Earl of Ross, Heber, Curtis, Harlow, Shapley, Hubble, Lundmark, Ronald, Sandage, Morgan, and de Vaucouleurs. And if you think about it, following this paper by Peng et al., clues to galaxy formation and evolution are probably buried in the details of galaxy morphology, which means it's probably a good idea to pay attention to details. However small they may seem, little details could mean something. And so I guess that's my point of view. And this is my goal with the series. Today I just want to mostly present a historical overview and illustrate the phenomenology of galaxy morphology and classification. And maybe not today, but one of the other lectures I'll talk about non-optical galaxy classification, and also the very dangerous subject of interpretive galaxy classification, where you try to impose a theory on how you classify the galaxies. It's a very dangerous thing to do. I would like to describe environmental impacts, of course, and there's something about the quantitative tools, because quantitative tools to interpret galaxy morphology, because ultimately you would like to have more than just descriptive morphology to interpret galaxies. And the subject of these large surveys, I mean, we live in an amazing time for galaxy morphology. Hubble could only have dreamed of what we have today. I mean, he could never have imagined what we would have. And then, of course, I'd like to highlight the importance and relevance of morphology to the evidence for secular evolution. We might have a thing like this, how is morphology relevant to secular evolution? Because it can be awfully descriptive. But I think it is the key to understanding processes of secular evolution, because galaxies are large systems of stars, gas, dust, dark matter, and they're susceptible to instabilities which can subject them to changes over long time periods. I don't know if you can see this, but we just saw, I think some of it spills over there because this isn't quite the computer that I use to make the slides. You could ask a question, you can ask a foolish question. There's the galaxy on the left. Is it possible it could change to the galaxy on the right? And how might it do that? So you look for, in secular evolution, you're kind of looking for relationships between different types of galaxies. You'll notice the galaxy on the left has a bar and a ring, and the galaxy on the right has a bar and a lens. The galaxy on the right has an outer ring. The galaxy on the left hasn't made one yet. I mean, could it make one? Could that galaxy on the left be environmentally affected to change into the galaxy on the right? So when we look at morphology, we're trying to find relationships between different galaxy types, and they may be there or they may not be, as the case may be. And you could also ask, if there is a relationship, is there a direction to it? Could it go this way, or is, heaven forbid, the other way possible? Probably not. But, you can certainly ask such things. Well, I wanted to start by just talking about the factors that influence galaxy morphology. There are extrinsic factors and there are intrinsic factors, and, they can affect how we see. The random orientations of disk planes, of course, affect the way a galaxy looks. Each one of these pictures shows a galaxy of similar morphology, and we can tell even though they're tilted and the inclination angles are below. And you go from a face-on ring-barred spiral that I put there because it's one of my favorite galaxies, and I love I love looking at galaxies like NGC 1433. It has its counterparts, 3351, 4274, and this is NGC 5792. And these are different inclinations, and you can tell they're basically the same kind of galaxy. in spite of the inclination. And then you get to a highly inclined one, like the one on the bottom, NGC 2654. And this is in a 3.6 micron image. I'll talk about those later. This one is tilted maybe 83 degrees or more, but you can still tell it has a ring. It has some sort of a ring, and so they all have rings, and we can still tell something about morphology in spite of this. But the differences are extrinsic. It's just due to the tilt. And the wavelength of observation matters. You can observe a galaxy in blue light on the left and look at that same galaxy in the near infrared, and it looks a little different because in the infrared you're penetrating the dust, and it's less sensitive to the star-forming regions in a galaxy, and so it looks smoother. Maybe this is the way galaxies were meant to be seen in the infrared, because we're penetrating the dust, and we're not being affected by star formation. The wavelength you observe them in depends. It affects the way they look. And of course, this is an intrinsic factor. The total mass and the luminosity of a galaxy has some impact on morphology. You can have a wonderful spiral like M81, absolute blue magnitude minus 21. Fabulous spiral, wonderful thing to look at. And then you have DDO 155 at absolute magnitude minus 12, is this little thing that with an irregular structure. You're not going to find a galaxy like M81 looking, you're not going to find a galaxy like DDO 155 looking like M81. Spirals of that absolute magnitude maybe don't exist. So morphology is sensitive to the total mass and luminosity. Also, I was going to say that when you look at a big galaxy, you can describe it by its rotation curve, its surface mass density distribution, its velocity dispersion. Those things characterize what we call the basic state of the galaxy. And that also matters to the morphology. And so total mass and luminosity are very important aspects for morphology. Environmental density, interaction, and merger history are also important. As we see on the left is the Coma galaxy cluster, a very dense environment loaded with what we call early type galaxies, ellipticals and S-zeros, and a couple of gigantic elliptical-like systems. They look totally different from these isolated spirals on the right, which are perfect spirals, the kind of thing you wouldn't find in the middle of the Coma cluster. So environment clearly matters. This is from the galaxies on the right are from the Amiga project, and that's an acronym for Analysis of the Interstellar Medium of Isolated Galaxies. And it's the project is led by Lourdes Verdes Montenegro. I put on the bottom left there some ancient footprints from Alabama. Our tetrapod ancestors from 300 million years ago left their footprints in Alabama, and the age of those footprints is equal to the look-back time to the Coma cluster. So that's just a little fun tidbit about Alabama. Of course, morphology is also sensitive to star formation history. When you look at galaxies that haven't formed any stars for billions of years, they tend to look rather different from the ones which have. And I'll talk about the Hubble types in just a moment. But star formation history matters to morphology. And of course, the expanding universe makes it a lot more fun. If you can look at morphology out at high red shifts, your ability to enhance your knowledge about the evolution of galaxies is clearly enhanced. And there are wonderful surveys like that picture on the left by Windhorst et al., which is a very, very deep 10-filter color image of a piece of sky. I think it's the Goods field. And when you look at some of the little smudges in detail in these kinds of images, you see these types of classes of high redshift galaxies that don't look like what we see nearby. So morphology is actually even more important now because we have to tie what we see on the right in those high redshift galaxies to what Hubble saw in his tuning fork. And that's one of the objectives of morphological studies, is to determine when did the Hubble tuning fork fall into place. So that picture on the right is based on many papers by the Elma Greens and others. Now let me do some historical background on galaxy morphology, because the history is interesting. It only became evident when people built big telescopes big enough to resolve some of the details of these faint nebulous objects called non-galactic nebulae. The early observers, like the Herschel, saw two types of nebulae, the galactic nebulae on the top and the non-galactic nebulae on the bottom. And they looked different. But the general suspicion, because this is in the 1700s, 1780s, 1790s, early 19th century, the general suspicion was that all nebulae were unresolved distant star systems, that all you needed was the big telescope to resolve them into stars. And so that was the general idea. And these non-galactic nebulae that were seen away from the Milky Way had a variety of interesting shapes. And here's William Herschel. He invented a descriptive classification, which could be called the first classification of galaxies. It doesn't matter that he didn't really know what they were. I mean, he had a good suspicion of what they might be. And one of the very few of these non-galactic nebulae that showed any detail was M51, and it showed a double ring system to Sir John Herschel when that was made in the 1820s. So there on the lower left is one of the first sketches of galaxy morphology. Now, these telescopes that the Herschels made, they were pretty good for their day. They were pretty big. But they couldn't, and you could discover thousands of these non-galactic nebulae with those telescopes, but they didn't reveal many details about them. Until this man here built the world's largest telescope. This is William Parsons, the 3rd Earl of Ross. He built at the castle in the middle, which is called Birr Castle, which still exists in Birr, Ireland. He built the world's largest telescope, which is shown on the right here, the Leviathan. That's a 19th century observatory. It had no dome. So if it rained, it got wet. And it had optics that would tarnish because it was exposed to the weather. And so he had to keep repolishing his mirror. It was a 1.8 meter speculum mirror. And even though it had the light gathering power probably of a modern 50-inch, it was good enough to reveal details in the non-galactic nebulae. So we call this huge telescope the Leviathan of Parsonstown. And you can find a replica there. And if you go back and look at the notes, which I did because I wanted to have fun with this subject, I want to write a book on the spiral nebulae, and I wanted to see where this was done. And I went there last year, and there's the current Earl of Ross. And that bottom left picture, his name is William Brendan Parsons. He's the 7th Earl. His ancestor was the 3rd Earl who discovered this. And if you look at the observing notebooks, they're just replete with details of galaxy morphology. Like, for example, you see here a bar surrounded by a ring. That's NGC 4725. It's the brightest of them all. You can see a bar and a ring. It's really neat. It's more than just spiral structure. And of course, that lovely sketch of M51 there is really a painting. And again, it's pre-photographic. It's not that photography didn't exist at this time. The telescope wasn't suited to it. So they had to make sketches. That's just a painting. It's not a bad rendition. Still pre-photographic era astronomy. And you look here on the lower right, NGC 2903. There's a poster out there on NGC 2903. The first observation of it showed Ansay bar. And then as they got better at looking at it, they saw a 4-arm barred spiral. So there are details of galaxy morphology in these early observations. It's very interesting. And if I could summarize what it is they found, what aspects of galaxy morphology did they see with this lovely telescope? The eyepiece was on the other side of the tube there, and only the walls are original. Everything else is a replica. Well, they saw bars and inner rings and pseudo-rings. They saw a bar Ansay, the little handles on the bar, and some 75 spirals. That's excluding planetary nebulae. They saw details in the spiral arms. They saw planar dust features, tidal features, and, believe it or not, Magellanic barred spirals are all seen at Birr Castle. Now, they didn't know these were galaxies. They didn't call them that. But the 3rd Earl built the telescope because he thought they were galaxies. He thought they were star systems. He wanted to resolve them into stars and prove it. He didn't resolve them into stars. He resolved galaxy morphology instead. And here's the first galaxy morphology atlas, believe it or not. You can even see some of your favorite galaxies in here, like NGC 4151 with its bar oval Ansay, which we just saw in one of John's slides. Some of these are planetary nebulae. It's okay. They couldn't tell the difference, really, but most of these are galaxies. So I consider this the first galaxy morphology atlas. They didn't assign Hubble types to these, but that's okay. It's still the first. It's very, very interesting. Now, you really got to get into the history of this subject. You have to get into photography. And photographic plates, dare I mention the word plate at a conference like this, because people don't take plates, but this was the way to do it. Now, this is astrophysics starting, the idea of having a telescope where you could take a long exposure photograph. It started in the late 1800s, and Isaac Roberts took this picture of M31 and discovered it was a spiral. And this is a very important photograph historically. The plates were sensitive to the blue emulsion part of the plates were sensitive to the blue part of the spectrum more so than the red, and so by default, galaxy morphology became a blue wavelength process. By default, they were the most sensitive plates at the time. So that's Isaac Roberts. And now, you imagine that you've accumulated enough plates that you can actually develop a classification system for these things that were called nebulae up until the 1970s. The term nebula was used at least until late 60s, early 70s probably, or at least till 1960. Max Wolf developed preliminary classification. People used it for 30 years. He had a little letter designation. It's hard to see because of the resolution of the screen. But you'll notice that at the top of his classification, there are amorphous galaxies that become quite a bit more complicated as you go to the bottom. Kind of a preliminary Hubble system, isn't it? And, well, with the limited plate material, they didn't have a million images to work with. They just had a few. With the limited plate material, this was good enough for most people who were doing galaxy work. So they had a progression of amorphous edge-ons to the spirals here, because part of it got cut off there. So that's Max Wolf's classification. Heber Curtis and James Keeler and Edward Barnard did a photographic survey with the Lick Crossley 36-inch reflector in the 1890s to early 1900s. And in 1918, Heber Curtis collected all the data. He interpreted the photographs, and he recognized this type of non-galactic nebula, which we know now to be ring-barred spirals. They were called phi-type spirals by him. And Hubble later renamed them barred spirals. So Curtis discovered them, I believe, at least he brought recognition to them. And then you see at the top there, and these are original pictures. This is from the original paper, NGC 1300. And then we saw the picture of 1300 from the Hubble Space Telescope. How could anybody live with such a thing? I mean, but this was cutting-edge research in 1918. So Curtis discovered the phi-type spirals, or at least he brought attention to them. Now, one thing that Curtis did is he knew there were lots of these non-galactic nebulae, and he estimated that within the reach of the 36-inch Crossley telescope, there could be 1 million such nebulae. And he believed that all of them would end up turning out to be spirals. That is, there were loads of these little things. If you just observed them with a big enough telescope, they'd all end up to be spirals. Hubble disputed that conclusion. He said, there are genuine bright galaxies that are not spiral. No matter how big your telescope is going to be, you're not going to see spiral arms in them. And so there's the recognition that there are objects which are spiral and aren't, and they're both the same kinds of objects. They're both these non-galactic nebulae. Of course, by the time of Hubble, he had already proved that these were galaxies. But as I said, the term nebula was still used. So Hubble proposed what we call the Hubble tuning fork. It's not his original classification. See, this Hubble tuning fork was proposed in a 1936 book called The Realm of the Nebulae, but the actual classification system was published in 1926. And it had the elliptical galaxy sequence here as a sequence of an increasing apparent flattening that would go into what he called the normal spirals, which were non-barred spirals. And most of the spirals that he found were of the non-barred type. Some barred spirals were found, they were put in a parallel sequence. He thought they accounted for only 20% of the spirals. So you could sort of think that the original system might have been ellipticals to normal spirals with a little bit of an offset here to get the barred spirals. But then he added the S0 galaxies because he thought that the transition from this highly flattened elliptical shape E7 to these types here was too catastrophic. There had to be something there to bridge the gap. And that's been disputed ever since. Sidney Vandenberg argued that Hubble's addition of the S0 galaxies to the classification destroyed the simple beauty of the original classification. And it did. And it's been controversial ever since. S0s probably don't belong there. But from a historical point of view, that's where they seem to fit. So after obtaining many plates, and Hubble had a little bit of guidance from Sir James Jeans, because if you go to James Jeans's very famous book, Astronomy and Cosmogony, published in 1929, he read Hubble's 1926 paper, and he schematicized it as kind of a tuning fork. And then Hubble maybe was influenced by that, but doesn't acknowledge it. Maybe that inspired him to lay out his classification this way. So anyway, the tuning fork is there, but it's probably not right, but it's okay. It still means something. Now, Alan Sandage used Hubble's notes to prepare an atlas that we can only call monumental. I mean, I'm here because I bought a copy of that atlas in 1969. And I have been interested in galaxy morphology ever since, so I really owe a lot to Professor Sandage here. Even though I have a little story to tell about my attempt to meet the man, which failed, but I owe a lot to him. He used Hubble's notes, collected the ideas, and Hubble was planning a revision because he wanted to put in these S0s. He had them in that little ball at the juncture of the tuning fork handles. Where do you go from there? So Hubble had developed a classification system of non-barred S0s, S0 sub 1, 2, and 3, and barred S0s, SB0, 1, 2, and 3, that would blend into the spirals. And Sandage also made this tuning fork a little bit more complicated because he decided it was relevant to recognize galaxies that were S-shaped, as John just showed us, and ring-shaped. And so the R variety are the ring-shaped spirals, and the S variety are the pure spirals of both non-barred and barred classifications here. So it's a more complicated system, and Vandenberg said this destroyed the simple beauty of the original system. So this is the revision in 1961. And I think the slides look a little jumbled because I'm using a different computer from the one I put this together on. Now, in the Hubble Atlas, the S0 class is laid out. This is what it is. There are three main features of what you might consider a normal S0. They have a nucleus, a lens, and an envelope. And the lens is this feature like John was just talking about. It's a feature with a shallow brightness gradient interior to a sharp edge. But it need not be real sharp. It's still there. It doesn't have to be real sharp. And in NGC 2784, it's got a lens here and a large envelope, and it's a prototype of what Sandage and Bedke and what would have been classified in the Hubble Atlas as S0 sub 1. So that's the structure of an S0 galaxy laid out. And there's a subclassification, S0, 1, 2, and 3, that's based on the development of increasing structure. From just a faint lens in the S0 sub 1s to more obvious structure in S02 to practically a dust structure in S03. So this is the revised, what we call the Carnegie Atlas, the revised Shapley-Ames, or the Hubble classification of S0s without bars. And I don't know how obvious it is on the screen, but this one here has multiple lenses, and it has no bar. there can exist more than one lens in a galaxy. Now, the classification of SB0s, you see this thing has messed up. This SB03A goes over here. The SB0 classification depends on the development of the bar from kind of a subtle feature to a real strong feature. And so that's the Hubble revision of S0 classifications. Now, at about the same time, and this is interesting here too, William W. Morgan, he appreciated the Hubble classification system, but he thought it could take into account stellar populations. The stellar populations are relevant to the Hubble classification. The stellar populations vary along the Hubble sequence, especially in the spirals. So he wanted to allow for the stellar population to be part of a classification. So he developed a purely morphological scheme of looking at the central concentration of a galaxy and deducing its stellar population. And he used these population groups, which are lowercase letters of spectral types. Spectral type A is a galaxy dominated by fairly early type stars, whereas spectral type K is a galaxy dominated by fairly late type stars. And then you have a whole bunch of categories in between, and that's what you do in morphology. You find one extreme and you find another, and then you put everything else in between. And so there's some cells that have sharp edges and others which don't. The ones that are in between don't. Well, in any case, so that's the main part of his system. And it's based on central concentration. And then he had some form families, the spirals, the barred spirals, ellipticals, irregulars, and this interesting category called D, which is sort of like S0 galaxies, but he didn't call them S0s, but that's what they are. But there's more to it than that. And then he had an inclination class, kind of like the number you see after the E in an elliptical galaxy. And if you take some color pictures, and you see, I guess I made a mistake in not using my own computer. It's just that I have memory problems in my computer. It could crash while I'm doing it. But here it's missing a few pieces, but I'll tell you what these are. This is a sequence of Morgan classifications. This is an AS4, a spiral dominated by spectral class A. Here's an AFS4 dominated by AF stars. Here's an FS4. Here's an FGS4 getting towards later type stars and greater central concentration. Here's a GB4, one with a bar, and here's a GKB4. And so the spectral classes are advancing from early to late type in these galaxies, and that's taken from his 1958 paper using Sloan Digital Sky Survey color images. And I think his method worked because I can see the differences that he recognizes. His is done purely by central concentration. He didn't have these lovely color pictures to help him deduce this. So the Morgan system nobody uses it much anymore, but it still had something to say. What people do use from Morgan is this, the CD galaxy. This is the most recognizable morphology from Morgan's system, the supergiant version of the D galaxies that you see in the centers of rich clusters. And I found these lovely images from the Sloan survey of these huge, huge objects in the middle of clusters. So this has survived, and this is what people mostly remember the Morgan system for. But his system was still useful. Now, in 1953, we had, I call him non-Palomar Firebrand because this man had the audacity to challenge some of the astronomers at Mount Palomar, and I know this was considered troublesome because I have talked to Alan. I've discussed this, not personally with him, but with Alan Sandage about what his views were about de Vaucouleurs, especially on issues of the distance scale work. But Gerard carried galaxy morphology into the southern hemisphere. He took some of the first pictures of well-known southern galaxies, and he wanted to classify them, but he didn't know what to do about the S0s. Because at the time he did this, it was the 1936 tuning fork, and the S0s are just this little circle with S0 in the middle of it with no details. So he went to Palomar to talk with Alan Sandage, who was working on the Hubble Atlas. And on the way, de Vaucouleurs developed his own classification. He took the tuning fork and he distorted it. So you have the handle. You have the handle of the tuning fork, which is the ellipticals here. And now you have, instead of just 2 prongs, non-barred and barred spirals, you have 3. You have the non-barred spirals, which are called S capital A, the barred spirals S capital B, and an intermediate category called S capital AB, and they blend together. But imagine that the tuning fork now has 3 arms, but you have to distort them at the other end, like this, bring them a little bit closer together, and then you swirl the prongs, and you get this. So that's why I call it the 3-prong swirling. It should be the 3-prong swirling distorted tuning fork, because you've got to bend the ends, and what the sound would be like, I have no idea with that. But so the way to think about it is that the usual types, like ellipticals, S0s, SA, SB, SC, are on the long axis of this 3-dimensional classification volume. And if you take a cut at each type, you find what are known as the varieties and the families. The bar strength and the ring spiral morphology are in the cross-section. So where would you look for secular evolution in this system? Would you look for it along this axis, along that axis, or a combination of both in some way? I mean, we're kind of looking for how things might move within that volume. But the volume it doesn't give an accurate impression of what's really going on. Why does it get narrow at the ends? Well, for example, the broadness has to do with the diversity of morphology at each type. In the middle of the Hubble, of the revised classification system here, stage SA, all these cells are filled fairly well. And they're fairly well filled even down to these stages, SB, SAB. They're fairly well filled. But when you go to some of these stages on this end, you stop seeing certain things. You don't see rings here, but you do see bars. Non-barred galaxies actually become rather rare on the right side. Barred galaxies become very, very abundant. If you go the other way, well, you have an elliptical. They don't have bars or rings, so it has to get narrow there. So that's why the ends are narrow, because the diversity goes down. But the volume doesn't tell you about the range of parameters at each type. For example, finding dwarfs in the middle of this volume is hard. Maybe they don't exist, but you can find things that are kind of dwarfish here and dwarfish there. So the parameter space is wide at the ends and maybe narrower in the middle. So this is a diversity diagram, but not a parameter space diagram. Let's see. Now, John has already showed this. De Vaucouleurs basically saw morphology as a continuous property, a continuous sequence of forms. He made this lovely sketch in 1962 on a cloudy night at McDonald Observatory, when I guess he must have been in a situation where he didn't have anything else to do. So he made this lovely sketch. If you want to know where it is, it's hanging in a place of honor in my office in Alabama. Eventually, maybe it'll go back to the University of Texas. Maybe it'll go into the archives of the American Astronomical Society. He didn't sign the darn thing because he maybe didn't think of himself as an artist, but I wish he had, because that's a work of art. But this picture shows the arrangement of what we call the families, which are the non-barred to the barred spirals, and the varieties, the rings, and to the non-rings. And this is near one cut through his classification volume. Now, how do you do these classifications? The way I like to do it is using the underline notation. This was developed by de Vaucouleurs in a 1963 paper. It wasn't used in the reference catalogs, but it could be used because bar strength, it seems to be a continuous parameter. From the non-barred ones, SA. So what you do is you define the extremes. You find the ones that have absolutely no bar and the ones that have the most obvious bar, and you find ways to squeeze in everything that seems to be in between. So the intermediate category was the S capital ABs. This was actually a brilliant addition to the Hubble system. That intermediate category allows you to be a little bit more specific about intermediate bars. If you want to determine bar fractions by visual classification, it might help to have an intermediate category that you could use. But you can also find intermediates between SA and SAB, which we call SA underline B, and between SAB and SB and SAB underline, and so you have a more complicated classification system. And then on the bottom, you can do the same thing with varieties. You can have a closed inner ring R and an open spiral S, and then you have an intermediate category called RS, and then you have these intermediate, sub-intermediate categories. And so it's a continuous sequence of forms. That's the idea. Now, the stage is the primary dimension, and elliptical galaxies, I'm just going to go a little bit through each of the stage, through some of the stage aspects. And the pictures don't show up very well here. But ellipticals are not supposed to have any structure. No lens, no bar. It just has to be a continuously declining brightness gradient. They should be obvious, but sometimes some S0s look like ellipticals, and you might misclassify them. There's loads of misclassification between E's and S0s. But with the best image material, you can do pretty well. The number is the parameter n. It was designed to be measured by I. Now, of course, we're fitting ellipses. We could, of course, make better values of En, but there's no point to it because the n has no physical significance. So En is already a problem with the Hubble tuning fork. It's a projection factor. It's an inclination class, but it has no physical significance. Now, what about this category? This is a stage called E+, which nobody ever uses. But E+ is meant to be a late elliptical in this system, something that sort of looks like it has S0 characteristics. And in the pictures, it doesn't really show it, but there's some subtleties in this galaxy that suggest it has a subtle envelope and a trace of a lens, which doesn't project very well, whereas that one's a genuine E3 galaxy. This is an E+ 3 to 4 over there. Now, this category E+ has some interesting occupants. You could have a galaxy that looks like a normal elliptical that may show traces of a lens, and then you have these galaxies, the CDs. These classifications of these three galaxies, CD, GE, giant elliptical, and CD are from Schomburg in 1986. In RC3, they're all classified as E+. Is this a good home for these kinds of galaxies? I don't know. Maybe they're in a class by themselves. Maybe these aren't really E+, but this is what they became to be known in the reference catalog. So you won't see the term CD in the third reference catalog. You're going to see E+. So their home in the third reference catalog is that category. But whether it's a good home for them or not, I think they're in a class by themselves. Now, the S0s here, this is getting to the problem, one of the problems with the Hubble tuning fork. In the spirals, the degree of central concentration is a classification criteria. For the S0s, it's not. The classification of S0s into these minus, S0 minus, S0, 0, and S0 plus categories depends on increasing visibility of structure. Like you might see a lens in that SA0 minus galaxy, and you see more of it in SA00, and in an SA0 plus, it's a downright ring. And so there's increasing structure until you get to the S0As, which look like a transition from S0s to spirals. On the bottom, you see the SB0 divocalar classifications going from relatively structureless barred galaxies to more structure in barred galaxies. And you can just barely see an inner ring in this barred galaxy. Now, some of these would be classified SBA in the Carnegie Atlas. Divocalar had a different point of view on the S0s. An S0 can have spiral structure, very subtle spiral structure. The families and varieties, you have R, RS, and S, they're carried into these stages. So you can have an SBRS0, and you see something that looks like a ring spiral, but it's still considered an S0 here. It's a different point of view. But you'll see this with the reference catalogs. That's what we're talking about. So you can have types like SBR00 and SBS0+, and you wonder, spiral arms, but they're very, very subtle features. But the Bose to disk ratio is not the classification criterion. Now, the spirals have 10 stages, and they're still defined using Hubble's three original criteria: the relative size of the bulge, degree of openness of the arms, and the degree of resolution of the arms into what used to be called knots that we now know are early type star cluster and star clusters and associations. But the problem is already evident with early type galaxies in that there exist small bulge early type galaxies. They don't fit into the stage. There's been a problem ever since. It's at the heart of all the problems with the Hubble tuning fork. Another thing that de Vaucouleurs did is he introduced what I call extreme late type spirals, SD, SDM, and SM. They're far more abundant than any of the other types of spirals. These are the spiral galaxies. They're these very, very late types. They can be very asymmetric. Now, here's a little sequence which I hope is visible of the different types at different families, but not at different varieties, just not to make it too complicated. But on the top row, you can see all the Hubble criteria. You see the large bulge, the tightly wrapped, low-resolution arms. You see the SCs with the small bulge, the open arms, high degree of resolution. The SBs are in between. And then you see the extreme late types that de Vaucouleurs added. The SD category was actually suggested by Harlow Shapley as an essentially something even more SC-ish than the ones that Hubble had recognized, until you get to the Magellanic spirals. And the bulk of the Magellanics are not of this type. They're down here of this type. They have bars. Bars are very abundant in that type. But anyway, even in these S capital ABs, you can sort of see the weak bars and the progression of the stages. But when you get to the barred spirals, that's where you run into trouble, because none of these galaxies here has a large bulge. They have what you see as a spot in the middle is a nuclear ring. And in the middle of that ring is this tiny thing. So the barred spirals, they don't really satisfy the criteria of Hubble's stages. But it's okay. It still works. I mean, there's still things you can do with it. Now, there are intermediate stages that you see. I didn't put them together because it would have been so long. But you have the intermediate transitions between A's and B's, B's and C's, C's and D's, D's and M's. And it turns out, and you do that at all the types, I mean, at all the families, and it turns out that the most common spirals in catalogs, not in volume-limited samples, but in catalogs, most common spirals are SB to SBCs. In volume-limited samples, the late types are going to be the dominant class. Now, a special hallmark of de Vaucouleurs' system is the recognition of the Magellanic Clouds as a late-type spiral galaxy. And you have the LMC on the left, the SMC on the right. They were always called irregulars. But even Sir John Herschel, with the naked eye, could tell the LMC was a spiral because he sketched it that way in 1847. So de Vaucouleurs considered these a distinct class of objects. It's a wonderful review by de Vaucouleurs and Freeman that laid out some of the properties of those late-type spirals. And then the Magellanic irregulars, they form the last major stage. And you can see that some of these have bars, like this. And you wonder, what does the S mean? There's some little squiggly something there that you never see an IBRM. You see IBSM because R's just aren't seen at these late types. Now, that hasn't been officially explained. Why are there no rings in late types? Is there too much gas? What's preventing the rings from forming? Is there not enough mass to form a ring? Anyway, these S shapes are due to little squiggles, and then some of them are just too low luminosity to even have that. And now down in the bottom are the I zeros, which de Vaucouleurs got into trouble for these. He put these RC2, the second reference catalog. These were assigned a type index. The de Vaucouleurs revised classification has a T index, a number for each of the Hubble types, each of the revised Hubble stages. There's a number. And there were these irregulars called irregular 2 by Holmberg. And things like these two here, this one here, this one is NGC 1705, and that's NGC 5253. They were irregular galaxies embedded in what looked like an early type disk. And so de Vaucouleurs put them at stage S0A, and that suddenly became the garbage bin of the Hubble sequence, where he was putting these galaxies into this place that people weren't sure. they belong. But the thing is, it's pretty obvious now where they belong. These are late-type galaxies embedded in spheroids, like the kind that John Corman, at least I think that's what they are. They're spheroidal galaxies that are still forming stars. They have embedded late-type they have embedded late-type galaxies in them. And NGC 5253 has an irregular in the middle of some kind of spheroidal galaxy. So they're a distinct class of objects, and maybe they're, I'm sure John will talk about the parallel sequence classification. Maybe those ones on the bottom are probably related to spheroidal galaxies. And the spiral and S0 stages are pretty obvious in the edge-on view. You can distinguish at least some of the types. It doesn't matter. It doesn't necessarily mean it's accurate, but you can still do it. And the spirals get a little thinner as you go from the early types to the late types. But one of the hallmarks of Hubble classification is you can still do something even in the edge-on view. You can say something about what kind of galaxy it is. Now, de Vaucouleurs was famous for assigning very detailed types to edge-on galaxies. He wouldn't just call it SC. He would call it SBSD spindle. And he got into trouble with that because in an FJ paper, he had classified the very large edge-on galaxy, NGC 4631. He thought it was a Magellanic late-type spiral. And Jeff Burbage wrote a paper claiming, you can't say that, it's only an SC. But people still look at edge-on galaxies, and we try to do better. And de Vaucouleurs was bold enough to try that. I don't know if he was right, but he did it. That's the kind of thing he did. Gave detailed classifications to edge-on galaxies. Now, in this picture here, you see the tuning fork arranged, and you can see the stellar population variations along the sequence, where you see the dominant late-type populations at this end and the early-type populations there. Now, it looks smooth. It does not mean that the order you see here is correct. It does not mean that. There is an ordering in the spiral sequence, and that's why the Hubble tuning fork is important, because the position along the arms of the tuning fork is sensitive to some physical aspect of the galaxies. It's a stellar population effect. The lack of bulges, the appearance of the spiral arms, they do matter. But on the left side, it doesn't necessarily mean that that's the correct arrangement. But it looks good, and it still means something. I mean, when you type something in this tuning fork, it still means something. But the order is an issue. And people are actively looking at that. Now, the outer ring classification, which John talked about, is the final part of the Hubble, of the Vaucouleurs Revised Hubble System. That's what VRHS means, the Vaucouleurs Revised Hubble Sandwich System. You find outer rings in non-barred galaxies. And, of course, you find them in barred galaxies, and maybe 10% of the galaxies have outer rings. But we don't know the exact frequency because it doesn't take much to lose them to galactic extinction. So you need to use infrared surveys to get the correct frequency of these rings. But one of the things that de Vaucouleurs did, first of all, de Vaucouleurs introduced the outer rings to the classification system, according to Sandage. And de Vaucouleurs also introduced these features called R prime, which are outer pseudo-rings that are made of variable pitch angle spiral arms. Now, a lot of these spirals have a ring-like character to them. Is it worth recognizing? And the answer is absolutely yes. R prime is one of the best things de Vaucouleurs did for galaxy morphology, in my opinion, in addition to his S capital A, capital B category. I don't know about the E plus category, right? I don't know if I'm going to put CDs in that category, but E plus is not on a level with R prime and S capital AB. So if you take these things together and you're given a galaxy that looks like this, which we've seen, how would you classify it in this system? Well, you put the pieces together like this. If it has an outer ring, and it does, you have the R, capital R brackets. You have this part. You look at the bar. And it has a bar, but it's not really bright. It's a nice bar, but it's not very strong. So you take that middle-of-the-road classification. It's not an S capital A. It's not an S capital B. Where is it? It's an S capital AB. So that's your bar classification. It has an obvious inner ring. That's your R classification. Then you put the stage, and then you got to say, well, it doesn't have strong spiral structure. It doesn't have much of a bulge either. But its classification is S0A, with a little bulge, which is already a problem, right? That's where the problems exist in the system. The bulge is inconsistent with the type, but nevertheless, I think that's the type it is. It just doesn't satisfy that bulge criterion. Now, you can be audacious. Why make this system more complicated than it already is? And, John has introduced lenses, and lenses are great. Lenses are very important features in galaxy structure, and you can see some continuity in them. So here, in the 1995 article called The Catalog of Southern Ringed Galaxies, I decided to follow John's example and recognize lenses in the classification. And here you have I'm trying to show here that you find them in non-barred galaxies as well as barred galaxies, and they come in degrees. You can see a pure lens, a ring lens, and a ring, and there seems to be some continuity. I don't know if it means anything, but you see some continuity. And the same is true for outer rings. You can find outer rings like in this galaxy here, and then you find outer ring lenses, and then you find what John called outer lenses. And so there's a morphological continuity between rings and lenses. Now, does it mean anything? Now, John has said that maybe lenses evolve from bars. Maybe they do, but maybe some don't. Maybe some evolve from rings. Could lenses be evolved rings in some cases? That's a possibility. Now, as John showed, I wanted to mention this again because I think John is probably the father of this subject. Would you agree with that? He's the father of this subject, secular evolution, because the title of his paper has the word secular evolution. I don't know if there's an earlier paper that says that. But in any case, he saw, as he pointed out, he saw the bars filling the lens in one dimension in NGC 1291. And this is NGC 3945, which has a bar like this, and it has a lens there, and it has an outer ring. And he suspected that the bar was evolving to the lens, into a lens through some process of possibly an interaction with the bulge. So that's one of the reasons why lenses are important. They're actually a poorly explained component of galaxy structure, but they've always been considered part of S-zeros. They were considered parts of S-zeros, so nobody bothered to recognize them. It was just considered an aspect of them you didn't need to recognize, but there's more to it than that. Now, the Vandenberg luminosity classes show the total mass effect. Sidney Vandenberg has been very adept at looking at absolute magnitude distributions through the tuning fork and trying to show that absolute magnitude distributions don't support some aspects of the Hubble tuning fork, like the position of S-zeros relative to spirals and E's. But he developed in 1960, it never really went much further than this, these luminosity classes, that he could distinguish a high luminosity galaxy from a low luminosity galaxy just by looking at a picture. And the way you could tell the high luminosity galaxies was how nice they looked. A nice looking spiral would be a luminous spiral, but a not so... Dare I should say that any galaxy isn't nice looking, because I find them all interesting. But some have more symmetry, they're more structured. And it's shown in these SC galaxies, where a luminosity class 1 SC galaxy, it's an SC1, is a very luminous, very structured spiral. And then you take the spirals which are low luminosity, like here, and then you try to fit everything else in between in these intermediate categories that are a lot like the stellar luminosity classes. So you have a supergiant spiral, a bright giant, a subgiant, and going down to S5 is pretty difficult, finding really low luminosity spirals. And he didn't have a standard that I could show in that category. And you can do the same thing for the SBs, except you'll notice there's no SBs here. They're just not seen. It's the late types you find the broader range in luminosity. I should say, too, that the luminosity class was once considered useful for the distance scale. People would use the luminosity class as a distance-independent index of absolute magnitude that they could use to get distances to galaxies. Now, it probably wasn't a very good indicator. Nobody uses it anymore. But at one time, it was, when people were desperate, especially de Vaucouleurs and Sandage and Tamman, desperate for ways of estimating the Hubble constant, they used these luminosity classes as a distance-independent indicator, a distance-independent luminosity indicator. And they worked at some level. Now, dwarf galaxies, they certainly widen the parameter space. And the categories shown here are dwarfs in the Virgo cluster. You have compact ellipticals here, and then you have what are called dwarf ellipticals. And nucleated dwarf ellipticals have an N, and you even have dwarf S-zeros, which is rather interesting. And where do you see these types of things away from the Virgo cluster? You don't find it as much. You find boatloads of these in the Virgo cluster. And then you have these BCDs, these blue compact dwarfs, small star-forming dwarf galaxies. And then the funny ones here, the large DEs, the large dwarf ellipticals, or maybe you could call them giant dwarf ellipticals, right? A giant dwarf, a GDE. They're seen in the Virgo cluster, too. And a huge question, and John has put a huge amount of effort into showing that these DEs are not the low luminosity counterparts or representatives of regular elliptical galaxies. Their progenitors are something else. The true low luminosity relatives of the larger ellipticals might be those compact E's, but not these DEs or DS-zeros. And he proposes renaming these DS-zeros, DEs, spheroidal galaxies. It doesn't really negate the value of this Sandage, Bengueli, Sandage, and Tamman classification. It's still useful. I mean, it certainly selects certain kinds of objects. But how you interpret them is another story. Now, detailed studies of these local group dwarfs, which are barely visible, I just show a couple of dwarf spheroidals. Now, that term was always used in the local group, and a couple of dwarf irregulars. They're so nearby, you can study their star formation history, and they have complex star formation histories in the local group. Now, here's a picture of what's probably a genuine dwarf spiral. This galaxy, IC 3328, is a DE in the Bengueli, Sandage, and Tamman Virgo cluster catalog. If you do a little image manipulation, you see there's a residual spiral, and it's downright cute. I mean, it doesn't have a bar, but it seems to be a genuine spiral in a very low luminosity galaxy. But 80% of the Virgo cluster galaxies are DEs, and there are very few that look like that. So it's still a very rare thing to see a dwarf spiral. So dwarf spirals are fairly controversial. But I wanted to compare a dwarf spiral with a colossus spiral. NGC 3928 is that little galaxy on the left there. It has a little ring that's 260 parsecs in diameter. And I'm comparing it at the same distance here with UGC 6614. See, this is 3928, and this is UGC 6614, which also has a ring 29 kiloparsecs in diameter. And there's very faint spiral arms. UGC 6614 is an example of a giant low surface brightness galaxy. And NGC 3928 is an example of a dwarf SB spiral. And it actually shows there is a huge range in spiral galaxies alone. People believe that these giant low surface galaxies have had low surface density of hydrogen that keeps star formation at a low level out in those huge disks. But this is just an interesting comparison between two spirals. Now, I'll just summarize in the last few minutes the tuning fork controversy. As I pointed out, the revised Hubble-Sandage and the de Vaucouleurs revised Hubble-Sandage classification system have always had a problem with the early types. The EN classification doesn't mean anything. The properties of S-zeros don't support putting them between ellipticals and spirals. There are some S-zeros that have little bulges. There's some S0As, SAs that have little bulges. They don't fit where they're put. And these studies here have challenged the tuning fork. A lovely paper by Cormandy and Bender where they resurrect the old parallel sequence idea of Spitzer and Buta, that S0s maybe belong in a sequence parallel to spirals, not between ellipticals and spirals. And this incredible Atlas 3D project where they use kinematics, not visual morphology, to examine the early types, and they could see the parallel sequence thing too. And then Laura Kane et al. In the Near-IR S0 survey basically came to the same conclusion that the S0s are derived from spirals. And so the tuning fork is in this controversy, but it's not new. But I was hoping this picture would look better. But this is an interesting revision that John and Ralph Bender have put together to deal with that EN problem, that EN doesn't mean anything. So the elliptical sequence is replaced with a sequence of boxy to disky ellipticals, and it's the disky ellipticals that could merge with the, of course, the S0s are still here in this diagram. That was 1996. He might not put them there now. But NGC, in most cases, when you look at an elliptical galaxy, I don't know if you can eyeball EB or EN or ED. I don't know if you can do that. Disky or boxy, I don't know if you can do that by eye. But in these two galaxies, you can. NGC 7029 is a boxy. I think it's an elliptical, but it has a little inner disk, so it's an EBD. And in NGC 4697, sorry about the slide. This is 7029. That's 4697. It's a disky elliptical, which you can tell by eye. But in order to tell these categories by eye, they have to be edge-on to see the disk. So if those two galaxies, the disks were face-on, you might not be able to put them into this sequence here. But nevertheless, it's a definite improvement over EN. And the boxy versus disky E's correlate with intrinsic properties, and that was the point of that arrangement. And then, as I said, further studies of these galaxies going back, and I should say that you're going to come to these conclusions if you do quantitative morphology. You need to analyze the brightness profiles of these galaxies to see where they really belong, and they're not low-luminosity elliptical galaxies. They're probably the offspring of late-type galaxies, those extreme late types. And here's Cormandy and Bender's rearrangement here, where they put the spheroidal galaxies, the old DE, DS0s here, next to the IMs. And there's a little bit of a stretch here from SC to IM that includes the extreme late types that may contribute to some of these in this narrow end here. And so the SPHs, so here we have the parallel sequence classification in the spiral sequence and the SPHs here. It's an interesting take. And there's Vandenberg's original suggestion with the anemic spirals between the stripped S0s and the spirals. But I should say, this is interpretive classification. You're not supposed to impose a whiff of theory on galaxy morphology, but that Vandenberg scheme there is imposing the idea that spirals can be stripped and modified to become S0s, with anemics, the A's, being partially stripped, partially depleted, gas-depleted galaxies. So there's a little bit of interpretive galaxy morphology in this, but it's okay. And then John showed he talks about, and this is a huge paper, absolutely huge paper, two kinds of E galaxies, the core and the coreless. And it's hard to see, but a core elliptical, it looks like it's cut off at the top, and a coreless elliptical has a peak at the top. And so it seems inconsistent with the naming convention, but it's historical. In the top panels, there are genuine ellipticals, and the bottom are spheroidal galaxies, and yet they look similar. So if you're going to distinguish them, you need to do quantitative work. And so those are the spheroidal classifications on the bottom. Okay, and the Atlas, I wanted to show this, but somebody else may talk about it in more detail. The Atlas 3D project used a rotation parameter to classify S0s. It's okay. You can do it by eye, or you can do it kinematically. And this rotation parameter distinguishes the slow rotators from the fast rotators. And in these papers, the authors were led to the conclusion that the parallel sequence classification was the right way to think of early type galaxies. Now, I can't go into detail about that. It's just a very interesting aspect of the problem. And I just wanted to say that none of this, as interesting it is, completely negates the value of the old classifications, because things like EN, S0, 1, 2, and 3, or E plus N, etc., they mean something. They still mean something. You may classify a galaxy like this and like that, and I guess you're seeing two pieces of information. They still are S0s, but you're looking at them in a different way. And, you know, the DE and DS0 categories, they're still historically relevant. So these revisions that I've just talked about represent the coming of age of quantitative and interpretive galaxy classification. So my last slide then just asks a few questions related to secular evolution. What does the continuity or the apparent continuity of galaxy morphology actually mean? Could an SB galaxy evolve to an SA galaxy and vice versa? Are lenses highly diffused outer rings? Highly diffused former rings. Diffused means they stop forming stars and over time they spread out. Could a bar dissolve into a lens? Could a pseudo-ring evolve into a closed ring? Can a galaxy with no ring become ringed? Maybe. And probably the most controversial one, could a late-type galaxy become an early type? And you saw all those steps along the Hubble sequence. Can you go from an SD to an SC to an SB to an SA? Probably not. But is there some way to do that type of thing? So these are the sorts of questions you can ask in the framework of galaxy morphology. They're not the only questions, but they're just some that you can ask right now. That's all. Yes.
Just a couple of comments to enlarge on what you've said. The business about the parallel sequence classification is not meant to challenge the standard Hubble sequence. It's a question of what you focus on at a particular time when you're asking particular questions, and it'll be the subject of my third lecture. A very short comment about Vandenberg's luminosity classification, because I suspect we're not going to come back to it. The astrophysical explanation that I think is best, it's in the literature, and you can look it up if you're interested in it, is a paper by Roberts, and Shu in, I would guess, the middle 1970s. 75. It's the only paper I know that were written by William Roberts, Mort Roberts, and Frank Shu. The other two comments have to do with confusions that keep happening in this subject that you touched on, that I just want to try and diffuse a little bit. And one of them has to do with lenses and the word lenticular galaxy. I really, really don't like the word lenticular galaxy. It was de Vaucouleurs' name for what I'm going to call S0s. And I think it comes from the fact that when you look at one edge on, like NGC 3115, it's got the shape of a lens. But that's got nothing to do, absolutely nothing to do with lens components. There are S0 galaxies that have lens components. There are S0 galaxies that don't have lens components. So he would call lenticular an S0 that doesn't have a lens component. And there's it's no wonder that people are confused, but I'd just like to clear this confusion up. So when you read the literature, you don't get confused again. Some lenticulars, some S0s don't have lenses. Some SB spirals do have lenses. Okay? Lenticular doesn't mean that the galaxy has a lens component. It's just an unfortunate word that comes from historically seeing a few of them edge on.
It goes back to Reynolds, 1920. Sure. De Vaucouleurs didn't invent the term. He simply used it like others have to describe
it. It comes from this historical fact that when you see an edge on,
they look like side view of a lens. That's right. That's how it got the name.
And the other comment has to do with CDs and Ds. And you're right, the CD phenomenon as an astrophysical phenomenon is the only part of the Morgan classification that's really still usable nowadays. The definition, Morgan's definition of a D, independent of C, was that it had a sort of a two-sloped light profile. The inner profile was steep, and there was a distinct outer profile that was shallower, so it looked sort of core halo. And of course, that's a description of an S0 that's face-on, because the disk is a shallower brightness profile than the halo. If you look at Morgan's Ds, the ones that aren't CDs, Morgan's Ds are mostly S0s, which you said, Ron. The CDs have the same character. They have a steep inner profile and a shallow outer profile, and they're astrophysically completely a different thing, right? They're objects that are brightest galaxies in clusters in which the outer shallow brightness profile isn't the disk, like an S0. It's the cluster background light. And that's a really interesting astrophysical phenomenon. And the C in CD, another little confusion, doesn't come from cluster, okay? It doesn't mean cluster dominant, which some people think. It's a holdover from the days when people doing stellar classifications used little c for superluminous. Supergiant. It doesn't mean cluster dominant. So it's a CD was to Morgan a superluminous version of a thing that's got a steep inner brightness gradient and a shallow outer brightness gradient. And by good fortune, he used that to identify something that we now know is really interesting astrophysically, and for that reason that term has survived. But most people who use it don't know what its origin is or why it's got this funny name. Just wanted to clear that up because you'll see a lot of confusion in the literature.
You mentioned at some point that the Magellanic-type galaxies do show a lot of bars. But yes. Are they the same kind of bars we see in giant galaxies? Because to me they look way different. Do you understand the question? So we see bars and you say there are many bars in Magellanic
galaxy.
But are they really the same thing we see in
spirals? You mean, are they fundamentally the same type of... Oh, no, they're very different. The late-type bars are not necessarily made of an old stellar population. I mean, they have an old stellar population, but they can have a very young population. They can be very thin. There are aspects of early-type galaxy bars that you just don't see in late types. Like early-type galaxy bars kind of have a fat central area. Looks kind of roundish. It looks like a bulge, but it's flat. It's probably a flat structure. You don't see those in late types. So Magellanic bars are a different beast, but they're still bars. Because remember, we're not supposed to put a whiff of theory into our classification. If it looks like a bar, maybe it's a bar, but it's another kind of bar. There are different kinds of bars. But late-type galaxy bars, they really are different. And when I say that extreme late types are loaded with bars, they're loaded with late-type galaxy bars, not the things you see in early types. And you don't see rings. They don't generate rings.
I wanted to ask something about the classification of the type DS0. Does it still make any sense to use it at the moment? Because we know that dwarf ellipticals almost all have an exponential profile, and S0 often comes from an envelope that people see.
Well, I'm not going to question Alan Sandage, but well, maybe I will, because the Vocalura always question. DS0s look like these dwarf ellipticals, but they have some structure that suggests that they should be classified as something else. But they're both exponentials, and of course that should be. It was known even long before people talked about some of the things I showed, that they were fundamentally different, and but it's still a classification. Maybe they're not dwarf versions of S0s. They're just things that look like dwarf S0s, but they're not really related to S0s. You won't find a DSAR0 plus type thing. They're very simplistic. But it's just the category they chose to describe it because those galaxies reminded the classifiers of S0s. But whether it was a good choice or not, I don't know. I think it's okay from a morphological point of view. From an interpretive point of view, it's probably not right.
All right. So if there are no questions, we should have coffee waiting for us downstairs, and let's come back here at 12. All right. So thank you.